And now we are going into our next section. We're going to hear from scientists who study animals you probably haven't heard of. And we're also going to, they also know the answer to the question, what history does a single drop of water hold? Top experts in exciting scientific domains share stories with us in our next Idea Boost. So first up, we're going to speak to the adorable and knowledgeable and incredibly interesting Cherisse Dupree, who mentioned and dangled the carrot of this presentation. That's going to be the big reveal of what she's got to show us. And so to the stage, please, Cherisse Dupree. She is the marine biologist and deep sea explorer, Fisheries and Oceans Canada with NEPDEP and the University of Victoria.
I'm back. Let's see. So the deep sea is often called the midnight zone because it is perpetually dark. It starts where the sunlight stops, around 200 meters, and extends down to a whopping 11,000 meters. It is 90% of the ocean. That makes it the single largest ecosystem on our planet. So what do we know of this most prominent ecosystem on our planet? Well, I will answer you not as a scientist, but based on these highly acclaimed natural history documentaries and the general public that they inform. So as I am repeatedly told, the deep sea is three things. It is barren, it is hostile, and it's trying to kill you. No, it's basically lifeless except for the monsters that are trying to kill you. So these deep sea monster narratives make it so much fun to try tell the public that they should love and protect the deep sea. But the narratives do help some people in the deep sea. There are emerging industries in our deep sea that thrive on the idea that the deep sea is scary and that there's nothing there. These industries advertise that the deep sea is our greatest ally in climate change, in combating it, and biodiversity loss. But it's only insofar as they are saying these are the places we should hide our mistakes, that out of sight is out of mind. So this is called burden shifting. It's not efficient, it's not safe, and I would argue it's not even sane to do this. So here are two examples from the North Pacific alone. Keep in mind that what we're planning to do to the deep sea here is in addition to fishing down the food web, which we already do, plastic pollution, dumping, the climate change effects that are already happening. So this is over and above it, and this is what the emerging industries suggest. So first, we would pull down carbon from the atmosphere, and we would dump it into the deep sea. So the pull down of carbon sounds like a great idea. So you would literally suck it out of the atmosphere, and you would get it. And then you're like, ooh, that sounds good. I would buy carbon credits for that. But the carbon is transported into the deep sea as liquid or as solid. It will do things like smother the environments, kill the animals, raise ocean acidification, deplete oxygen, and have mass cascading effects on the animals that live there. So this is the questions you need to ask if you're like, oh, I'm gonna buy some carbon credits. Maybe not until science figures out a way to mitigate all those things. So the second example, and my least favorite, is deep sea mining. So I try to tell you about these industries with like as little sarcasm as possible because I'm trying to give them a fair shakedown. But deep sea mining essentially is, we need batteries, we need metals, they're in the deep sea, let's go get them. And so what happens with deep sea mining is you have to target seamounts, underwater volcanoes, hydrothermal vents, superheated areas, or the nodule abyssal plains. You would send down a tractor, it would literally churn everything into a slurry, animals and rocks alike, 100% mortality of everything that lives down there. If that's not bad enough alone, that activity stirs up all the carbon that has been settled in the sea floor. It makes these toxic plumes that then move around the bottom of the ocean. What gets sucked up to the ship waiting above is that slurry to be refined, and valuable things go to the shore, and everything else gets dumped back over the side. So now you've got surface or mid-water plumes that are hundreds of kilometers, toxic, potentially radioactive if it's hydrothermal vents, and this is going to affect whales, sharks, seabirds, turtles. So not just hidden in the deep, but the entire water column. And this is, the sales pitch on this one is a green future with the lightest planetary touch. That's like quoted from the website. Okay, so does this sound familiar? It should, because we know the plot. We know machines of mass destruction. We know what happens to the wildlife and habitats when the machines move in to get a resource. Okay, so I have to implore on you that the deep sea, a healthy, functioning deep sea, is essential. If it wasn't for our deep sea, this planet would actually be Mars, and you could see how well that worked out for Matt Damon. So the reality is life on this planet exists because of the deep sea. And so basically my science and all the outreach I do is to give the deep sea a much needed glow up because we need it. Okay, so now, okay, so the deep sea supports all life on our planet. And I can tell you firsthand that descending into it is like going back in time. It is the most natural, timeless environment on our planet. It is beautiful, bustling, and vibrant with an endless cast of characters. Did you know that there is so much life in the deep sea that bioluminescence is the most common language on our planet? Did you know there are more corals in the deep than there are on tropical coral reefs? Did you know that the longest lived animals are in the deep sea? The sharks can be 500 to 600 years old. The corals, 4.5 thousand years old. The sponges, 10.5 thousand years old. Did you know that because of the stability of the deep sea, rays, skates, like we just saw there, have survived the 5 great mass extinctions of our planet? They existed 450 million years ago. That is 100 million years before trees showed up on our planet. Did you know that the deep sea seafloor is as complex as our landscapes? It is a great mosaic of underwater mountains, rivers, hot springs, desert plains, lakes, valleys, hills, canyons, you name it, we got it down there. The deep sea is, in fact, our greatest ally in combating climate change and biodiversity loss. But the key to this is that it is slow and steady down there. It is natural and timeless. Thanks to the deep sea, our climate on this planet is stable. Thanks to the deep sea, we experience seasonal change. We have weather. The oxygen from the ocean is every second breath we breathe. Did you know that this deep sea octopus sits on its eggs for 4.5 years, fending off predators and making sure the water circulates around the eggs so that they're healthy? The deep sea is natural and timeless, and it is the engine behind the stability on our planet and all life. It is not barren, it is not hostile, it is not lifeless. And if we do not change the storyline, we will be the monsters in the deep sea. The end.
Wow, thank you, Cherisse. I did not know any of that. Up next, Eddy Carmack, Senior Scientist Emeritus, Ocean Sciences Division, Institute of Ocean Sciences, Fisheries and Oceans, Canada.
Well, okay. Everyone here knows now that the climate is changing. But what exactly is changing? It's more than polar bears and sea ice. What's changing is the most unique and beautiful system in the entire universe. Now, let's start with a fearless fact. Write this down. There are 60 million billion drops of water in the ocean. Just ask Cherisse. She'll confirm that. Now, why in the world is that important? It's because these little guys are the worker bees of the climate system. And here's how that works. The climate system actually has a job description. And that job description is to get excess heat that comes in from the low latitudes, ship it to the high latitudes where it can be lost back in space. And who does this work? Well, water. Water in ocean currents, and water is moisture in the atmosphere, inexorably moving heat poleward. So whenever a drop of water leaves the ocean, condenses, falls as rain, it's doing its job. And with 6 trillion drops of water heading north past Newfoundland every second, they're doing their job. So when we mess with this system by burning carbon and putting up aerosols, we mess with this beautiful, unique system, the only one in the universe. For example, let's look at what one drop encounters as it does its job. Now, I'm not a filmmaker, but I read Bill Cosby's PhD thesis about Fat Albert, and he says if you got a story to tell, you start with a hand-drawn storyboard. So that's where I'll start. Here's my storyboard. There's a map of the world, and we're going to follow that drop of water as it moves around the world, starting in the North Pacific, and it's doing its job and serving all of us. So somewhere in the North Pacific, a little drop of water is born. It might have been a bright sunny day or a cold and stormy night. Now she joins trillions of other drops of water traveling east, northeast toward Canada. Of course, she really doesn't form a drop when she comes out of the water. She has to meet up later with aerosols and particles, but that's another story. Traveling on, many of her traveling companions fall as rain as the winds rise and cool over the coastal and Rocky Mountains. And they eventually drain back into the Pacific through our streams and salmon-bearing lakes. But our little hero carries on, crossing the Great Continental Divide before falling into a lake. I could go on. I will go on. Let's say she makes it to Tutoti Lake. Tutoti Lake, the headwater lake of the Great McKenzie River Basin. Imagine being the headwater to an area that drains an area the size of Mexico. By now, she's 6 days old. Now the next slide. Now the long journey begins. As she flows down rivers through strings of reservoirs that's generating the power that we're using today, crosses lakes, river deltas, goes through the Great Slave Lake, the deepest lake in North America, and finally reaches the shores of the Arctic Ocean. This has been an exhausting run, and she's now about 30 years old, having overwintered in 2 or 3 lakes along the way. Now the rules change. Next slide. No more westerly winds. She's now in an ice-covered ocean under the clockwise blowing Beaufort high winds. Now these winds blow in such a way as to collect her and all her companions into a low salinity bulge in the Arctic Ocean. It's 300 meters thick. I could go on. Now we'll go on. The bulge is a bit of a chubby bully in that it slowly constrains the upward flux of nutrients, and that makes the Beaufort Sea low in biological productivity. But it also constrains the upward flux of heat from the deep ocean, and that protects the ice cover. So she's still doing a job for the climate system. Eventually, after a few trips around this Beaufort merry-go-round, she escapes the Beaufort Gyre and sneaks out by our Northwest Passage and into the Labrador Sea. Now she's about 70 years old and back at work. Now she enters the North Atlantic, where she rides the cold Arctic outflow current, which, by the way, helps protect eastern Canada from nasty hurricanes. But that's another story. Now things start to change. Her cold, slow-flowing Arctic current collides with the warm, north-flowing Atlantic waters from the Gulf Stream, creating a mixture so dense it sinks all the way to the bottom of the sea. Wow. She's now part of the global thermohaline circulation, which is the greatest climate engine on Earth. Upon entering the North Atlantic, she's now about 80 years old, same as me. Being part of the thermohaline circulation may sound exciting, but actually it's a bit boring because it's such a long and slow journey. And the action is like warming and cooling and biological production is taking place at the surface. I could go on. I will go on. Our hero is now multitasking. Next slide. She's working for the ocean's food web. How? Picture an old slow-moving locomotive. The death, sinking, and decay of biological particles over so many years is loading the slowly moving train with life-supporting nutrients like nitrogen, phosphate, and silicate. She travels on down the Atlantic, around South America, around South Africa, India, and Australia. But this long and slow journey is also drawing down oxygen and making the ocean more acidic. So this balance is critical, the rate at which this all goes on. Slide. Now our little hero is back in the North Atlantic, where she started. And the winds are working to bring her to the surface. She's rich in nutrients and ready to fuel the food web and ready to start that climate journey again. She's now 1,000 years old. And it's the year 3024. Yeah, but wait. Next. What kind of world does she enter? Will she see a clear and pristine sky like the one she left behind? Has she remembered from all her past journeys? Or, retracing this journey, will rising temperatures have completely altered the Earth's evaporation and precipitation patterns? Will the westerly winds that carry rain to our forests and salmon-bearing lakes and streams and fields of wheat have weakened and shifted and sent moisture elsewhere? Will the boreal forests rivers and lakes of the Mackenzie burned or dried up? Will the Beaufort ice cover be gone, allowing all the animals, along with all the animals that once lived there? Next, will the slow and steady thermohaline circulation that once regulated our climate so perfectly have just given up, allowing our oceans to go anoxic? 1,000 years from now. Okay, go back 1,000 years on her previous journey around. Just as she was passing Scotland, Macbeth was killing King Duncan. And Lady Macbeth was spreading blood everywhere to dodge the blame. So people will ask, what were we thinking? I could go on, but I won't. Thank you. and do good things.
Thank you so much, Eddy. And now we have the wonderful Alyssa Gehman, research scientist with the Hakai Institute and adjunct professor at the University of British Columbia.
Good afternoon. I've really enjoyed getting a window into the work that is going on in your industry, and I'm now going to give you a window into the work that I'm doing. Is my presentation up? Yay, excellent. So I'm going to talk to you about why I, as a scientist, study animals that you may not have ever heard of. So these are all animals that I study. Some of these may be more familiar. We've got a sea star, we have some crabs and hermit crabs up there. But I'm going to start by talking to you about these orange blobs that are on the crabs and the hermit crabs. And these are parasites. And this parasite is actually a castrator and a feminizer. So it castrates and feminizes the host that it's on. And one of the reasons to study them is just that that is fascinating and totally intriguing. How does that work? What is happening there? Another reason to study animals is because something drastic or huge or obvious is happening to them. So this is a sunflower sea star. You can see a diver in the background for scale. These are huge sea stars. They're really big. And about 10 years ago, we started to see them looking really sick. So they're twisting. You can see this arms are twisting back on themselves. We would actually, after this stage, maybe one arm would drop off and walk away. Then we would see lesions forming. They'd start to dissolve, and then they would completely dissolve away until all you could see is just this little pile of mush that used to be that sea star. And this was happening at an incredibly rapid pace. So these pictures are actually from near here in British Columbia, from early October 2013. On the left, you can now see a pile of sea stars that used to be there. By the end of that month, they went back to the same location. They were all gone. So just really fast. And this was happening at the whole range of where these sunflower stars live. So the colors are just places where we have estimated how many of the population were lost. If you look down towards the south, some of those numbers are 100% as far as we know. As you go further north, you can see that it gets a little more hopeful. We only lost 90% of these animals. When we put that number together, that was actually 5 billion sea stars. And it happened so quickly. And so one of the reasons to study them is just, how did that happen? What happened? It's really alarming. But the reason I study these animals is because I'm really interested in this question of how climate change is going to affect disease, just as in a whole general question. One of the amazing things about disease is that we can use sort of the same math, the same science, to study diseases no matter what host they're in. And you might actually have an idea about this from COVID. So one thing we can do is look to see how contagious new diseases are. And you can see we have common flu, COVID-19, and measles. And you can see on the little numbers there, we have 1.32 and 15. Those are R-naughts. That's how contagious this disease is. And you can use this to look across different diseases in humans, but you can also use it to look across different diseases in just anything that gets a disease. So going back to our barnacle, well, it's actually a barnacle parasite, I didn't tell you that, but the castrating parasites that I talked to you about earlier, we can look at the temperature dependence of that transmission potential. So looking at that R-naught, that same metric we use for COVID, you can see that how transmissible these castrating parasites are is temperature dependent. So on the x-axis, we have sort of colder to hotter temperatures. And you can see that there's a hump-shaped curve where around 15, maybe between 15 and 20 degrees, that's really a contagious period. But as we get above 25 and 30, those animals the parasite is less contagious. And in fact, what we found, these animals are actually from Georgia, the state in the US, so it's a really warm location that they came from. And actually, eventually, the parasite is removed from the system with high temperatures because it can't handle those high temperatures, which leads to fun media coverage, like the next slide, where we say climate change is good for these crabs, potentially, because it removes their castrating parasite. It's one way to interpret it. Interestingly, that temperature dependence, that curve that I showed you, is also true for mosquitoes, and there are many, many parasites that get into humans. So all of these different rainbows are different mosquito species with different human parasites. So we've got West Nile virus, dengue fever, Zika, all sorts of things in there. And so we can see similar patterns and similar trends. And that leads to news articles where actually for dengue, because of their temperature dependence, we may actually expect to see more dengue fever in future climate. Next slide. Which takes us back to those sea stars that I told you about. We're just beginning to understand the relationship between the disease that killed them and temperature, and the things that we can learn from those relationships will inform not only how we protect and manage this species, but it may actually inform how we understand how climate change is going to affect diseases that affect you, affect your community. And so that's one reason that we study animals you may never heard of. And I will just want to end by saying, I gave you one reason. There are many other reasons, and hopefully you can dig into that for for future work in science. So thank you so much for listening, and hope to talk to you later.